We start. Okay, good afternoon, everyone. Welcome to this edition of the NITheCS Colloquium. My name is Francesco Petruccione. I'm the director of NITheCS, and this afternoon I'm very happy to introduce Dr. Graeme Pleasance, who is a postdoc here in Stellenbosch in our group. So Graeme did his PhD at the University of Sussex with Barry Garraway. So very famous PhD supervisor, and then he came here to even more famous postdoc supervisor. No, I'm joking. And Graeme, after his PhD, he moved to UK as a 10, where I was based at the time. So it was pre-COVID and post-COVID. We translated him to Stellenbosch. So Graeme, I'm very happy that you are here today and you volunteered to offer a talk on the history of open quantum systems. So Graeme, please, over to you.
Okay, there we go. Okay, yes, thank you to Francesco for that introduction. So yeah, so the title of my talk is a brief history of open quantum systems. So yeah, let me just start by saying thank you for also taking the time to come. Okay, this is gonna work. Yeah, so let me start by maybe just giving a brief background of myself. So as Francesco said, well, I should say that perhaps most people know Francesco through being the director of NITheCS. He's also the lead of our group. So our quantum at Sun group based in the physics department here at Stellenbosch, so of which I'm part. So our group has around, this is a very rough guesstimate that I tried to put together. The numbers always fluctuate, but this is about the average. So we have around 4 postdocs, of which I'm one, about 9 PhD students, and I think 1 master's student. This is a not so relatively recent picture of us at Chapman's Peak. I only chose this picture because I'm actually in it. We have a lot of other pictures that I'm not in. So this contains like some people in the group and some people not in the group. So, but yeah, our group is relatively diverse. So we have a relatively broad range of interests. So we work on kind of various aspects, I guess, what you can categorize under the umbrella of quantum control and technologies. So we work on quantum computing, quantum machine learning, open quantum systems, which obviously I'm going to talk to you today about, and a little bit of quantum thermodynamics, which I may or may not talk about at the end. Okay, so this is just a very broad outline. I should say that the title of this talk, A Brief History of Open Quantum Systems, is a not so subtle rip-off of A Brief History of Time. So my kind of intention was to try to come up with a very broad kind of pedagogical idea of what open quantum system is and some kind of chronological development of the theory. I realized that that's a bit of an ambitious goal to give in the space of an hour. So what I've done is kind of come up with like a broad overview of the idea of open quantum systems theory that does contain some technical stuff, but hopefully which isn't too boring. And then within that, I've kind of sprinkled in some kind of historical context. And then towards the end, depending on time, I'll maybe talk a bit more about my own research, which is on kind of applications of open quantum systems theory to quantum thermodynamics and also kind of the development of non-perturbative methods. Okay, so I should maybe start by just saying, like, what do we actually mean when we talk about open quantum systems? So as the kind of, in a very basic sense, as the name suggests, it's an open quantum system is a quantum system that is open in the extent that it can exchange energy, it can exchange information, it can exchange entropy with other things. So that other thing we call the environment, okay? And so to the, to the extent that any kind of physical system that we can interact with in the real world, almost by very nature, is open, right? Otherwise, we wouldn't be able to kind of acquire information about it. So in that sense, a theory of open quantum systems is a theory kind of about everything, since as far as we understand, the world is described fundamentally by quantum physics and quantum mechanics. And so therefore, it's a theory about everything, but not necessarily of everything. And so because it's kind of universal in that sense, finds many different applications. So these are just some applications that I've listed. So one of these is to kind of quantum optics, so describing light matter interactions, which is, I think, historically where open quantum systems were kind of most studied or kind of developed historically. Also, as I mentioned, to quantum thermodynamics, so looking at how we can characterize things like work and heat and entropy at a quantum level. So quantum computing, maybe some of you are more familiar with, quantum information processing, also quantum biology, so etc. Okay, so that gives a kind of motivation of why we should be interested in open systems. So I thought I would give maybe kind of, I'm assuming a kind of lay audience, so I'm assuming there's people here who necessarily aren't physicists or maybe don't have much background knowledge in kind of quantum mechanics. So I thought what I would do is give a kind of brief illustration of some of the main kind of concepts of quantum mechanics. So at a kind of basic level, it's a theory that allows us to describe the fundamental behavior of particles and things at generally like a very small scale. So things like particles, atoms, molecules. So a key aspect of quantum mechanics is that it's an inherently probabilistic theory. So it's a statistical theory. So it doesn't, if we say, for example, have a quantum system and we measure it, the theory doesn't tell us exactly what measurement outcome we will get. It gives us a probability of giving a certain measurement outcome. So fundamentally, as far as we understand, fundamentally the outcome of measurements or experiments are random. And so the way that we calculate the probabilities of obtaining a particular measurement outcome is different to how we do it classically. And so for that kind of second point, I thought I would try to kind of illustrate that basically with the following experiment. So this is kind of the well-known double slit experiment, for those of you who maybe already know. So we have this kind of experiment where we have a particle which is emitted from some source. So we can think of this as like a single electron or something, which passes through this kind of two slits that we call 1 and 2. And then we can potentially measure this or detect this particle on this kind of screen here using this kind of detector. And so what we can do is say, okay, if we can potentially measure the particle at any point on this plane after it passes through these two slits, and we just call the distance away from this kind of central line where we detect the particle, or we label it by this kind of coordinate x. Okay. And so if we assume that that this particle behaves kind of classically, then we can kind of make the following or we can assume the following two statements are true. So when I say that this particle behaves classically, what I mean is its physics can be described using the laws that we apply to the laws of physics that we apply to the everyday world, so at the macroscopic scale. So for example, if you want to describe how the trajectory of a tennis ball or something like that. So if we assume this behaves classically, then these two must be true. So we can say, okay, well, the particle can kind of go through either one of these two slits that we call 1 and 2, or 1 and 2. And the probability of it arriving at some point x on this screen So P of X should be the sum of two probabilities of it either going through either one of these slits. So here P1 just gives the probability of it going through slit 1. P2 gives the probability of it going through slit 2. So if we consider the case where we kind of block one of these slits, so only one of these is now open, so say slit 1, then say we run this experiment many, many times. So an electron is emitted from this source, it goes through slit 1, and it can arrive at some point on this screen. Okay, and so if we run this many times, we can think of there being kind of many detection. You can think of it, a detection event, as corresponding to a sort of a light, a small spark of light on this screen. And so if we run this many times, there'll be many kind of dots on this screen where we detect the presence of this particle. And so kind of what this line here represents is the kind of the expected distribution of this particle if we block one of the second slit. And so naturally we expect it to be more localized in this position than, say, for example, all the way down here. Okay, so then the other kind of, the second case we can say is, okay, if we then block the other slit, just by symmetry argument, you can say that, well, okay, if we do the same thing, if we run the experiment many times, this is the kind of the expected distribution that we call P2. And so if we have the case of just using the kind of simple laws of probability, then in the case where both the particle can pass through either one of these slits, then the expected distribution would just be the sum of these two kind of distributions, P1, P2. So this is what it looks like. So it's kind of centered around this dashed line. But in fact, if we do this experiment with real electrons or real kind of other types of particles like photons, this isn't what we see. We don't get something that looks like this kind of bump. What we get is an interference. We get some kind of pattern that looks like this. So it's a kind of pattern that contains many peaks and troughs. And more kind of importantly, it basically represents a distribution that isn't just the sum of these two distributions, P1 and P2. And so kind of what this distribution is kind of reminiscent of, though, is kind of like a wave-like interference pattern we get when we, say, for example, observe kind of ripples of waves on like the surface of a water. So that's kind of what this GIF here is kind of shows kind of the excitation of kind of two water waves. And then you can see that as the waves kind of disperse, there's points where the waves kind of destructively interfere. So these are these kind of like lines here where you see there's no waves. And then there's points where the waves constructively interfere. And so these correspond to these kind of fringes. So these points of constructive interference correspond to these peaks. And these points of destructive interference correspond to these troughs on this diagram. So this kind of illustrates to us that there's this kind of fundamental wave-like behavior that particles display that can't be described using classical physics. And so to kind of address this, what we can do is, instead of speaking about kind of probabilities in this sense, in the classical sense, what we can do is introduce the notion of what's called a wave function. So this is just kind of an object that allows us to kind of to fully characterize the statistics of all the possible kind of detection events on this screen. So more specifically, the probability, this distribution here, is given by the modulus squared of this wave function. So inherently, this wave function is a kind of complex quantity. And so why that's important is because it allows us to characterize, the fact that it's complex allows us to characterize this type of interference phenomena. So more specifically, the modulus squared of this kind of wave function, if we can write this wave function as the sum of the contributions from these two slits, so this is kind of otherwise what's known as a superposition of two wave functions, then the modulus squared of this gives us kind of these two contributions that look like the probability of the electron going through either slit 1 or slit 2, but also this additional component that kind of characterizes this interference phenomena. Okay, so essentially the takeaway of this is that if we want to describe fundamentally how things like electrons and photons work, we have to describe their behavior using wave functions, which don't really have a kind of classical analog. So I should also emphasize that the notion of classical probability is still relevant in quantum physics in the sense that you can interpret this kind of the modulus squared of a wave function as a probability measure in a classical sense. It's just the way that we calculate these probabilities is inherently different for quantum mechanical systems than as we do classically. So essentially where this law isn't obeyed. Okay, so that's kind of a kind of conceptual overview. So proceeding now to kind of talking about or going towards the idea of talking about or formulating open quantum systems, what we can do is, what I can do is try to introduce some of the kind of the mathematical machinery behind how we describe quantum states. So let's just consider a kind of relatively simple system. So like say, for example, a spin half particle, such as an electron. So this is kind of an example that people like to use because it's an example of a quantum system that can, if we just only take into account its kind of spin degrees of freedom, it's a system that can only occupy one of two states. So this kind of is meant to diagrammatically represent our particle. So it's just, I won't go too much into what spin is, but essentially it's kind of an intrinsic form of angular momentum that particles have. It's a vector-like quantity, so this arrow is kind of meant to represent geometrically the spin. And for a spin half particle, its projection along, say, the z-axis can take one of two possible values, so plus h bar over 2, which we call the spin up state, or minus h bar over 2, what we call the spin down state. So how we can mathematically describe the system is using a kind of wave, as I said, the wave function or a wave vector. Just for simplicity, I'll use these terms interchangeably, although, yeah, this kind of wave function I introduced previously is kind of formally as a kind of projection of this wave vector onto real space. But essentially, this thing just describes the same kind of statistical behavior of our quantum particle as the wave function does. And so for this kind of two-state system, we can generally write its state like this. So just basically as kind of like the sum of spin up and spin down. You can just think of this as a kind of complex two-dimensional vector. And so this state kind of sits on, for those of you who are mathematicians, this is effectively, we can mathematically say that this state is an element of some kind of vector space or complex vector space or Hilbert space. The reason that we describe these states using Hilbert spaces is because they kind of endow our quantum states with properties that we like. So, basically like the sum of any two states is also a valid state, the fact that these states are normalizable, etc. And so, as I mentioned, these kind of quantum states have an inherently probabilistic interpretation. And so these coefficients, what they tell us is that, or is the modulus squared of these coefficients gives us the probability of this, if we measure the particle, of being in, like, say, for example, spin up state or spin down state. And because they are probabilities, they have to be normalized. Okay, and so we can also measure, so we can represent, so here we can represent what are called observables. So essentially observable is any kind of quantity that we may be interested in measuring about our system. So for this example, when we're only thinking about spin, an observable, a relevant observable would be, for example, like the z component of the spin. Mathematically, we can represent these kind of observable as matrices. So this is just an example of like the spin, the z component, or the observable corresponding to the z component of spin, which can be represented in terms of the Pauli Z matrix. And we can calculate, so as I said, fundamentally quantum mechanics is probabilistic. So we can kind of calculate, if we, say, prepare a spin half system in a particular quantum state and then measure the system, its Z component spin many times, we'll get a bunch of measurement outcomes. And then what we'd like to do is characterize the statistics of those measurement outcomes. So that's what's encoded in this psi. And so, for example, like the average value that we expect for our Z component of spin can be computed in this way. So this is just kind of computed in the same way that you would do with the classical probability. So it's just the value of the spin times by the probability of it being in that state. And so just using a little bit of mathematics, you can show that this can kind of be represented in this way as kind of like the inner product of this quantity with the state psi. Okay, and so yeah, just to kind of emphasize what this kind of state characterizes is the situation where, say, for example, we have our system in this state, we measure it. After we measure it, we either get a measurement outcome of plus or upspin or downspin, which correspond to these values plus or minus h bar over 2. So say, you know, we have a kind of an ensemble of such systems. So basically many identical copies of this system. We measure one of them, we get a value of spin up. We measure another one, we also get a value of spin up. We measure another one, we get a value of spin down, etc., etc., etc. So what we'll then do is, you know, if we measure each of the particles in this ensemble, we can then obtain a kind of collection of measurement outcomes. And what this state characterizes is basically the statistics of this ensemble. Okay, so that's just to kind of emphasize again this kind of inherently probabilistic interpretation of quantum mechanics. Okay, so something that's kind of really crucial for when we talk about open systems is how quantum states evolve in time. And so here's where maybe I start introducing a little bit of history. So as maybe some of you already know, the way that we can describe how quantum systems evolve in time is through something called the Schrödinger equation. So this is effectively just a differential equation that tells us how our state psi changes with time. And so this historically was as the name of the equation suggests, it was introduced by Schrödinger in, I think, 1925, although I think it was published in 1926, but it seems to be either 1925 or 1926 that it was introduced. And so it depends on this kind of object that we call the Hamiltonian. So basically, I mentioned that kind of quantities that we can measure about our system can be represented as operators. And so this kind of Hamiltonian operator, this hat kind of represents an operator notation, basically represents the kind of the energy observable. So its expected value gives us the average energy of our system. Okay. And so let's just kind of consider the spin half example again to see how this equation tells us, or how the Schrödinger equation tells us this spin evolves in time. So we have our spin half. Let's say that this spin is then subjected to a external field, like magnetic field along the x direction. And that at some kind of initial time that our system is prepared in a state which is just a superposition of spin up and spin down. So here I use this kind of z index to indicate the fact that this is the z component of spin. Okay, so the magnetic field is in the x direction, whereas this represents the z component of spin. Okay, and so a kind of Hamiltonian that characterizes this type of situation would be something like this. So it basically is it's the type of Hamiltonian that characterizes like a kind of dipole interaction between the spin and the magnetic field. So this kind of quantity mu here is like the spin magnetic moment of the electron, and this B is like the external field. And so if we assume that this is just along the x direction, then this can be written in terms of this Pauli x operator. And so this omega is also sometimes called the Lamour frequency. Okay, and so if we just put this into this kind of Schrödinger equation, we basically get this. Well, this is one kind of equation that we can get out. So basically, this just tells us how the probability of our system being in the spin-up state changes with time. Ooh, sorry. Okay, and so we can kind of just solve this equation. So this is just a particular example here that I illustrate that, you know, the case where we say, for example, that our spin starts in the spin down state. So with probability 1, it's in the spin down state, so hence this kind of C down is 1, C up is 0. Then what we get is effectively this kind of plot on the right-hand side. So this kind of blue line is basically the solution to this previous equation that I just showed. And so you can see that what happens is that basically our the probability of this system being in spin up just basically oscillates indefinitely with time with a particular frequency. And so that's kind of characteristic of the type of behavior that the Schrodinger equation describes, this kind of coherent oscillatory behavior. And so what I've also plotted in this diagram is this kind of what's represented by this orange line is basically the expected value or the mean value of the x component of spin. And you can see that this basically just is constant with time. And so this is actually, for this particular example, the reason for that is because our Hamiltonian is just equal to this Pauli X operator. And so this, in a sense, this time derivative basically gives us the expected value of the energy, how that changes with time. And for this type of example, basically what this is saying is that the average energy doesn't change with time. And so we can kind of formulate, or we can actually prove that more formally. And so, okay, what I should also importantly say is that the fact that, so the Schrodinger equation, in this example that I gave, the average energy doesn't change with time. You can prove more generally that the Schrodinger equation, by construction, conserves the total energy of our system if this kind of average energy is time independent. Okay. And that's important because what that tells us is that the Schrodinger equation, what it describes is basically how closed systems evolve in time. So essentially the opposite of open systems. So systems which don't exchange energy with its surroundings, don't exchange information with its surroundings. And so, as I said, you can kind of prove this more formally, that the Schrodinger equation kind of conserves total energy. So again, just using a small amount of mathematics, you can show that this is if this operator H is time independent, then its expectation or mean value is also a time independent quantity. Okay. And so, okay, the way that I do this is just by the definition of an expectation value is like the same in the classical sense. You just times so this En represents a possible energy value that our system can be in. This represents the probability of our system being in a particular energy value. And you can write this in this kind of particular form. And then that just basically gives you this answer of 0. So as I kind of said, what this Schrodinger equation describes is a system whose energy it's a system who doesn't lose energy with time. And similarly, so this kind of characterizes energy conservation. And similarly, it describes a kind of reversible time evolution. So maybe if I just quickly go back to the previous slide, so to here, the evolution of our spin under this external field kind of undergoes this oscillatory behavior. But what could happen is that if we just stopped the time evolution of the spin at some arbitrary point, we could in principle then apply another type of Hamiltonian whose sign just changes by a minus factor. And then what would happen is our system would undergo the reverse time evolution. So it would say, for example, we stopped it here and then just then applied another type of time evolution, but with a minus Hamiltonian. It would basically just follow back the same path. So that kind of characterizes time reversibility. So these two kind of aspects of the Schrodinger equation, so energy conservation and reversibility, are things that don't generally apply to open systems. So, in the real world, when we kind of look at systems, they tend to dissipate energy to their surroundings. Similarly, according to kind of like the laws of thermodynamics, things tend to exhibit irreversible behavior. So this just kind of tells us that this kind of Schrodinger equation description isn't a way that we can describe the time evolution of open systems. So we have to introduce some kind of modification of this framework to be able to do that. So one maybe other approach you could say is that, well, can't we just make everything closed? Um, so say you have like some system of interest, like the spin half example. If our spin half isn't a closed system, what we could do is just extend our system to potentially the entire universe, assuming the entire universe is a closed system, and then say, okay, then we can then use the Schrodinger equation and other things to then describe how this system evolves in time. The problem with that is that generally that's kind of a really intractable way of doing things, because say all we care about is the behavior or the properties of this spin half particle. We don't want to have to include the description of the entire universe in that. So in other words, we don't want the global description of local behavior. I mean, also excluding the fact that it would be incredibly complicated to describe. So what we want is we want a framework or a theory that just describes how our quantum system evolves, that takes into account its interactions with kind of the external world, but doesn't have to include everything. And so kind of how about open systems? So as I said, generally speaking, an open system will exchange energy with its environment, so its total energy isn't conserved. Similarly, according to this kind of picture, this environment is something that we generally don't have any control over. Typically, it could be some kind of macroscopic system that could be, say, for example, in thermal equilibrium. Generally speaking, in physics, we tend to find things tend to evolve into equilibrium states. And so in this case, our environment would exhibit some kind of thermal fluctuations. And so for an open system, these fluctuations what they do is they introduce kind of noise into our system. And so what this then infers is that we have to come up with some kind of description or framework that accounts for this kind of extra randomness that is introduced into our system as a result of it being open. And so neither of these two things can be really properly captured in a purely Schrodinger type framework. Okay, so what I'll do is I'll kind of explore, well, actually first, kind of regarding the second point, talking about noise, what we can do is kind of come up with a generalization of the notion of quantum states that accounts for kind of additional noise. So rather than just consider, say, a single quantum state, which is what we were doing just a few slides back, what we can do is consider kind of a statistical mixture or sort of an ensemble of quantum states, which are kind of mixed according to some particular weight, which you can also potentially interpret as a probability. And so what I mean here by kind of statistical mixture is, say, for example, I have a kind of a coin, and I have a machine, and I flip this coin, and depending on the measurement outcome of this coin, I prepare a particular quantum state and give it to you. If in that kind of experiment, if you don't know, if I say flip this coin, if you don't know the measurement outcome of that coin and I give you this quantum state, its state cannot be described just in terms of a single kind of wave vector. It would be described in terms of a kind of a mixture of wave vectors which are mixed according to each of these weights, which would, in this kind of coin flipping analogy, correspond to the probability of say, a coin flip of heads or tails. Okay, and so again, just a little bit more mathematics. So if we want to kind of compute going back to the spin example, so again, the kind of the expected value of the Z component of the spin, then we can still compute that in the same way as we did before when we are now dealing with the kind of mixtures of quantum states. So again, this is just the probability times by the particular value, the probability of being in a particular spin state times by the value of that spin, or the Z projection of the spin. What we can then do is make use of the notion of conditional probability. So here we can say that the probability of, if we measure a system of getting a measurement outcome of either spin up or spin down, is basically equal to the probability of getting this measurement outcome conditioned on our system being in a particular one of these states with a particular weight pi. So this just follows from the definition of conditional probability. You can then rewrite this in this form. And so what you can then do is come up with a kind of slightly more compact notation for this kind of object, which can be represented in terms of a quantity which is known as a density matrix. Again, I won't go too much into kind of the mathematical details, but the idea here is that what this density matrix is it's kind of it's an object that, like the wave function, fully characterizes the statistical properties of our system, but also accounts for kind of more general ideas of quantum states. So more generally, it can account for kind of statistical mixtures of quantum states. So the previous example that we were looking at, which is the case where this pi, there's only one possible value of I, and this pi is 1. Okay, and so this kind of notion of what's called a density matrix was originally introduced, I think is what's usually attributed to John von Neumann. So it was introduced in this this work on kind of the construction of quantum, the probability theoretical construction of quantum mechanics. Although something that I'll touch on in a few slides is that actually there's kind of independent sources that also introduce this idea of a density matrix. Okay, so kind of just to say is that if we want to talk about states of open systems, we generally have to kind of rely on this density matrix description, not on a kind of single quantum state description. Okay, so going back to our kind of spin half particle example, how can we describe its behavior as an open system using this kind of density matrix formalism? So one kind of approach to doing this is, as I said, the Schrödinger equation inherently conserves energy. So what we can do is just say, okay, let's just phenomenologically into this equation just introduce some kind of terms that cause dissipation of energy or cause damping. So one kind of way of doing that is with this equation. So here, this kind of part here is just the equation that I gave on the previous slide, so the one that you get from the Schrödinger equation. These two kind of terms that depend on these kind of what are called rates gamma, these kind of describe kind of damping effects. And so we just introduce these phenomenologically. We haven't come up with a kind of particular reason. We just say, okay, let's just do this phenomenologically and see what happens. And so what we can do is kind of rewrite this. We can do the same thing, but for the density matrix of our system. So kind of a more general kind of way of describing the quantum the state of our spin half system. So here, or I should say that this density matrix, like operators, is a matrix, and as is inferred through its name. And so this here represents kind of like one of the components or one of the matrix elements of our density matrix that corresponds to kind of spin up. So this is just equal to the mod squared of this. So it just this thing here just equals to the probability of our system being in the spin up state. There are also these additional components like here, like rho up down. So these kind of represent coherences in our system. So these are terms that kind of can describe interference phenomena between different spin states of our particles. So analogous to how I described at the beginning of the lecture, where you kind of have this interference effects. So this is kind of intrinsically quantum behavior. Okay, so you can kind of phenomenologically, for the spin half example, describe the open system, the time evolution of our system in an open sense by introducing these kind of phenomenological damping terms. And so here, this kind of gamma E, gamma A, so this subscript E here references the fact that this corresponds to an emission rate, whereas this gamma A kind of corresponds to an absorption rate. And if we assume that the kind of the damping in this case is induced by kind of thermal fluctuations, then these rates are going to be characterized, or these rates can be given in the following form. So this emission rate can be written like this. So this n here is kind of just what's called the Bose-Einstein distribution. But but the point is that these thermal fluctuations can correspond to a particular temperature of the environment that we call T. Okay, and these equations, this is kind of like a simplified form, but these equations are what are sometimes called the Maxwell block equations. Okay, so they're basically a phenomenological set of equations that describe the open dynamics of a spin half particle. And so if we then, like we did before, we can just solve these equations and then look at the time-dependent behavior. So this kind of gray line that I show in this diagram is what we had previously. So the case where we just had a kind of an external magnetic field along the x direction applied to our particle. So that just comes from this term. So this gray line corresponds to the case where this gamma E and gamma A are 0. So again, we just get these coherent oscillations. But now when we introduce these damping terms, we get kind of the behavior that we would more naturally expect from the types of systems that we observe in the real world. So we get this kind of damping. Our system no longer kind of coherently oscillates, assuming that it's prepared in the spin down state. The probability that it's in spin up grows with time and then kind of flatlines. So this blue line corresponds to a case where this omega value is non-zero. I don't know if you can see it. I maybe should have used a better choice of colors, but there's kind of an orange line here and a kind of a red dashed line. This orange line corresponds to the case where this omega is 0, but we have non-zero damping rates. And this kind of red dashed line corresponds to the thermal populations that we would expect in thermal equilibrium. So you can see that these kind of match kind of exactly. So this thing here just you know, from classical thermodynamics, if we have a system that's in contact with a kind of a thermal environment, there's a probability of it being in a particular energy state. And so what this basically just tells us is that these equations are kind of consistent with the type of behavior that we would expect from the second law of thermodynamics. So basically we put our open system in contact with some environment that exhibits some kind of thermal fluctuations. Then what happens is that in our time, over time, the system just gets damped and then effectively approaches thermal. In the case where we have no driving, our system just approaches thermal equilibrium with the environment. So that's kind of the behavior that we would naturally expect. So in a sense, that kind of also answers why we introduce these particular terms into the equation. It's because they basically give us kind of the answer that we were looking for. Obviously, this requires a kind of element of knowing the answer actually is. Okay, so historically, these kind of equations are quite important. So, so the Maxwell block equations. They're also analogous to another set of equations which are called the block equations. So these block equations are slightly different in that, so these describe the behavior of a single spin half. What these block equations describe is basically a similar setup but for a kind of ensemble of nuclear spins. So basically they can be used to describe nuclear magnetic resonance. So when you have a kind of ensemble of nuclear spins that undergo thermal relaxation. Okay, and so these kind of block equations were introduced originally in this kind of paper, so of 1946, so a reasonably long time ago. Okay, so this is kind of like a phenomenological way of taking a time evolution that describes a closed system and then just making it open by just introducing kind of phenomenologically damping. So this is kind of the approach or the approach that underlines these so-called block equations. So this work was done in 1946. But what I also wanted to kind of highlight is that the history, this is where the more historical part of my talk comes in. So that, you know, historically there's actually been some work done that kind of significantly predates this kind of introduction of the block equation. So in one kind of work that I wanted to highlight was this kind of really early work of Lev Landau, which was on this kind of damping problem in wave mechanics. So assuming that, you know, the Schrödinger equation was introduced in 1925, it only took, you know, a year, 2 years at most for people to already start trying to apply this into kind of the context of open systems. And so this is the paper. So what he does in this paper is he basically employs a kind of open system framework to describe the or to derive the spontaneous emission rate for an atom interacting with an external electromagnetic field. And actually in this paper, I've read it. It's actually, well, at least for me, it's a little bit difficult to read because it uses a lot of notation and terminology that's very dated. But to my understanding, that Landau actually kind of independently introduced the notion of the density matrix in this paper, kind of in parallel to von Neumann. Okay, and so these are kind of some other notable examples that, well, this is meant to be kind of an approximate timeline that kind of notes some kind of important developments in developments in formalizing the idea of open quantum systems theory. So this, I should say that this list is by no means complete, but it's just some kind of examples that I wanted to mention. So there was this work of Landau on looking at how you can describe spontaneous emission of atoms. There was a work slightly later by Wigner and Weisskopf, which also looked at a similar problem of describing the spontaneous emission of an atom interacting with a quantized electromagnetic field. So a similar type of problem. There were these block equations which I mentioned. There was also the introduction of this so-called Bloch-Redfield equation. So this can be thought of as kind of a generalization of the Bloch equations in that it uses what's called a system reservoir model to kind of derive an equation, what's called a master equation. So a master equation is something that characterizes an open system time evolution, and in fact, like this kind of equation kind of contains the Bloch equations itself. So this is kind of like a more formal derivation of these Bloch equations, and not done phenomenologically. And then also another kind of important contribution was through kind of Feynman and Vernon. So I'm sure maybe some of you know, like the path integral formalism of kind of quantum mechanics is a kind of very well-known formalism that was originally introduced by Feynman in the 1940s. So this was a kind of application of this path integral formalism framework to specifically describe the behavior of open quantum systems. So originally it wasn't introduced in an open systems context. Okay, and so the reason I kind of highlight all these kind of these other contributions in this kind of orange coloring is because they all kind of rely on this idea of what's called system reservoir models or microscopic models. So previously when I mentioned this kind of phenomenological introduction of damping, we just did this in a kind of very ad hoc way. We just introduced some kind of terms and said, okay, they describe spontaneous emission or thermal relaxation. But what you can do is kind of come up with a more rigorous formulation where we actually introduce a new kind of system into the framework, which we call a reservoir of the environment, and we treat this in itself like as a quantum system in itself. And so this is what kind of underpins these so-called system reservoir models. And this is actually kind of the most, I'd say the most common kind of formalism that's now adopted to treating kind of open quantum systems from a theoretical point of view. So I'm not sure how much time I have left. So I don't have a huge amount of time. So maybe 10 minutes, okay. So I'll just try and describe some of the ideas that underpin these system reservoir models kind of briefly. So if we kind of just go back to this kind of picture that I had, so we have some kind of quantum system of open system of interest that we assume can exchange energy and information with its environment. So what we can do is say, okay, let's just assume this environment is basically the whole universe, and then treat this kind of combined system as being closed, which is kind of, so I mentioned this kind of previously as one approach. But what we can do is, rather than describe the whole kind of system and environment together, what we can do is come up with a mathematical way of just looking at our open system, but which kind of explicitly incorporates or I should say implicitly incorporates the interaction between the two into the description. And so we just we proceed in the kind of in the same way that we do for closed systems. So the total Hamiltonian of this setup is basically just so as I mentioned, this Hamiltonian object characterizes kind of the energy of our system. So if we introduce the Hamiltonian of our open system and environment, we can basically split it into these kind of three contributions. One is kind of corresponds to the energy of our open system, one corresponds to the energy of our reservoir environment, and one corresponds to kind of an interaction component. And so this is not something I'll go over in detail, but the way that we can kind of describe states on this kind of global space is using this kind of tensor product notation. So more formally, states of our entire system are basically written as the tensor products of states of these two subsystems. So in a kind of maybe slightly intuitive sense, what this just tells us is that you know, consider the basic case where we just have a system that can only have two states. Say we have an environment that can have two states, then what this just tells us is that the kind of combination of these two states gives us four possible states for the space of our kind of combined system. But anyway, okay. So I mentioned the fact that our kind of starting point with these system reservoir models is to say, okay, we just take our system and environment and then assume that this thing is closed. So because it's closed, its time evolution can be described by the Schrödinger equation. This is just the same Schrödinger equation that I gave previously. We can rewrite this in a kind of density matrix notation. So I won't go into the details of this, but effectively, these two things are just analogous to each other. So this thing here is what's called the commutator. So basically, it's just equal to the Hamiltonian times by rho minus rho times the Hamiltonian. Okay, but this basically describes the time evolution of both our system and environment as a whole. But as I kind of mentioned, we don't really, we just want a description that just looks at our system. We don't want a description that also takes into account everything the environment is doing. But similarly, we want a description that kind of accounts for the interactions. So kind of mathematically, how do we do this? So one way of doing this is through introducing this notion of kind of what's called reduced density matrices or reduced states. And so as I mentioned, this density matrix kind of, you could interpret it in the same way as a wave function. So it characterizes all the statistical properties of our system. It tells us with what probabilities that we will obtain particular measurement outcomes when we measure our system. So what we can do is consider kind of, okay, say again we have a spin. Say we have a system that is just a spin half, so it can occupy two states. Then we can just look at, say, the expected value of the Z component of the spin like we did before. Well, we compute this expectation value on the kind of the global space. So not just the system alone, but also with the environment. But where the kind of this object here is kind of what's called the identity. So it's kind of like just a trivial operator for our environment. So what this kind of represents is basically the expected value of the spin, but where we basically we're not really measuring what the environment is doing. So like before, this is just exactly the same as before. You can write it in this form. This just kind of comes from the kind of use of classical probability theory. And then what we can do is rewrite it in this form. So this is equivalent to the expression I gave for the expectation value before, but now it's written with respect to this other type of object, which is called this so-called reduced density matrix. The reason it's called a reduced density matrix is because it's a density matrix, but it just characterizes the statistical properties of just our open system, not of the environment. And so you can obtain this through a kind of mathematical operation that's known as the partial trace. So this is kind of formally how this kind of reduced density matrix is defined. But the kind of the takeaway point here is that this object gives us a full statistical characterization of just our system without having to look at properties of the environment as well. Okay, and so how much? Okay, 5 minutes. So again, I won't go into too much detail at this point, but once you kind of have introduced this idea of this reduced density operator, you can then, like the Schrodinger equation, say, okay, if we want to understand how our system evolves in time, we just come up with some equations of motion and then solve these equations of motion. And so you can do that using the Schrodinger equation, but then using this partial trace operation to kind of average out or kind of throw away the information that we have on our environment. And so that's what's kind of contained in this equation. Kind of one common approach to trying to solve these equations is what you do is so I should just say, okay, I won't go into the kind of technical details of this, but this kind of I subscript represents a kind of what's called an interaction picture representation, but I won't go into the details of that. But this object here on the right-hand side is the density matrix of our global system. The object on the left-hand side is just the reduced density matrix of our system alone. One way we can attempt to go about solving this is by basically integrating this equation for the total density matrix and then reinserting it back into the same equation. This may seem a little bit pointless, but it kind of offers us a starting point to try to introduce some kind of approximations that allow us to simplify the description. So here I should actually say that this should be a 1 over h bar squared, so that's a bit of a mistake there. But so kind of importantly, what distinguishes this kind of system reservoir description compared to the phenomenological description that I gave before? Because you could just look at this and say, okay, well, this seems a lot more complicated. I mean, yes, it is a lot more complicated, but importantly, what the system reservoir description allows us to do is to actually kind of capture effects of system reservoir correlations. So as our open system evolves in time, it will become correlated with the environment in some way. And what we would like to do is capture the effect of those correlations because they can potentially have a quite significant impact on the time-dependent properties of our open system. Unfortunately, it tends to be very difficult to do this. It's generally a kind of very non-trivial problem of how to describe the evolution of an open system interacting with an environment under arbitrary conditions. But this kind of approach can serve as a starting point for introducing certain approximations. So one of these approximations can be something like, okay, we assume only weak interactions between our open system and the environment. And kind of potentially the implication of that is that we can factorize the density matrix of our open system and environment at all times. And so this is kind of quite a popular approach and actually relates to this kind of Bloch-Redfield equation that I mentioned previously. So so this type of equation with a few additional approximations can be used to, say, for example, describe the relaxation of a spin half system under a thermal environment. So effectively capture the same type of physics that I gave in terms of these phenomenological Maxwell-Bloch equations before. And so this kind of is, give a bit of a plug for Francesco's book. So this is all in Francesco's book, if you're more interested in that. But just to kind of emphasize that this kind of system reservoir approach is speaking in terms of modern applications of open systems. So I've kind of talked about kind of historically some kind of important ideas and concepts. So this system reservoir approach is kind of the framework that's most commonly used now, specifically for this fact that it allows you to kind of much more rigorously describe things and also kind of capture effects of system reservoir correlations. Okay, I basically have no time left, so I mentioned at the beginning some kind of interesting applications. Some of the applications I mentioned here were to kind of describing light matter interactions. There are kind of many other kind of more modern applications. One of these is to, say, quantum computing, but there's also, say, quantum biology. So I won't go into this because I don't have time, but for those who are interested, there was like quite a nice mini school given, I think last month, by Bethany Adams, who's also a postdoc in our group, on quantum biology that involved some kind of application of open systems ideas in this context. So if you're interested, I encourage you to look at that. So some of the work that I do is more on the kind of the domain of quantum thermodynamics, but also looking at how you can describe systems that, say, strongly interact with their environment or are strongly correlated with their environment. So I probably don't have enough time, but kind of one very interesting application, kind of quite modern application of open systems theory is in this quantum thermodynamics context. So, classically, thermodynamics is a kind of framework that describes things such as work, heat, entropy. So as the name suggests, quantum thermodynamics is a kind of an extension of these concepts to a kind of microscopic domain. So, classical thermodynamics tends to apply to descriptions that are made up of macroscopic numbers of particles. What quantum thermodynamics is interested in doing is saying, okay, can we take these kind of ideas and scale them down to potentially very small systems that contain a relatively small number of particles? Are we able to characterize things like heat and work and entropy in these types of systems? Kind of one application of interest is to the development of what they call thermal machines. So I'm sure most of you are familiar with things like refrigerators, cars. These are kind of clear kind of technological applications of kind of classical thermodynamics, which was formulated in kind of the 19th century, gave rise to kind of the Industrial Revolution and all the kind of the things that spawned out of that. So kind of one idea is that can we kind of build these thermal machines like heat engines, in the context of like cars or whatever, but can we scale these down to like to individual atoms? Can we build a refrigerator using a few atoms or something like that? And so these are kind of some interesting work that's been done in the last 10 years or so. So this field, I should say, is a relatively new field, but there has been some kind of a seminal experimental work that's been done in the last 10 years or so. So this is one such example, which was looking at the implementation of what's called an Otto cycle. So this is a type of thermodynamic cycle using an ion trap. So basically, in this system, like the ion is the working medium, so it's the thing that you can use to extract work from. And the idea of this Otto cycle is that it has kind of 4 phases. One phase where you inject work, one phase where you extract work, and then 2 other phases where your working medium, or ion in this case, thermalizes with respect to either a cold or a hot reservoir. And so what they basically did here was kind of demonstrate, it was an experimental demonstration of kind of a microscopic implementation of an Otto cycle using a single ion. This isn't something that you can really call a quantum thermodynamic cycle, since in this type of experiment, the ion was in effectively a thermal state throughout the cycle. So it was kind of a microscopic implementation of a semi-classical heat engine. So more recently, and to the best of my knowledge, this is the kind of the first experimental demonstration of what you could call a quantum heat engine. So this was using nitro vacancy centers in diamond. And what they did was implemented various types of a continuous and 2- and 4-stroke variants of an Otto cycle. And they implemented this in a regime where, for a particular type of model, they showed that you can, compared to kind of a classical heat engine, gain some kind of quantum advantage. So specifically, you can have a higher power output of your thermodynamic cycle in something that's called the small action limit, which I won't really elaborate on. But to my knowledge, this is kind of like the first experimental demonstration of a quantum thermal machine. And so this was kind of written up in this kind of physics journal article. So if you're interested in it, I encourage you to look at that. I've pretty much run out of time now, so I was going to talk a bit more about what I do, but yeah, we can skip that. So let me just end by then saying thank you.
Yeah. Thank you very much, Graeme. Are there questions for Graeme? Please.
Thanks for your nice talk. I just would like to understand that whether we always need the concept of environment to study the concept of decoherence. Suppose we have a quantum system in a given space time. So whether the space time itself behaves as a role of environment.
So you don't necessarily. Let me try to go back. So you don't necessarily I guess that relates kind of, let me just stop here. So that, I guess this relates to these two descriptions that I gave. One is this kind of phenomenological description, and the other is this kind of system reservoir model. So you said, do you need an environment to describe kind of classical or decoherence? So I would say no. You can just say, for example, if you have a system that's subject to some type of classical noise, this would give rise to classical decoherence. So some kind of uh, damping that destroys quantum coherence or kind of.
How to distinguish between the classical decoherence and quantum decoherence? What is the key?
I would say that
point?
one way you can do that is that if you want to describe quantum decoherence, you'd have to use a kind of system reservoir model, which explicitly uses a quantum representation of your environment. So yeah. So an environment which potentially, because I guess the thing that distinguishes, like, say, for example, classical and quantum decoherence is that quantum systems or quantum environments can have vacuum fluctuations, which classical systems can't. And so this can give you a kind of decoherence at 0 temperature, which you can't have classically.
Okay.
Yeah.
Okay. Thank you.
Any other? Yingxue, please. Donovan, you have to do your 10,000 steps.
I have 3 questions. One is your H equation. There was a H equation which get to 0. Maybe the previous one.
This.
Yeah. So then, for the first line, partial t psi h psi h t, and then how did you get into the second line?
This. So I guess you just use yeah, you just this is just equal to the derivative of this first side plus the derivative of the second side.
Oh, okay.
So then you just use the definition of the Schrodinger. You just apply the Schrodinger equation to this.
Yeah.
And then you get
just failed third year quantum mechanics exam.
Well, I haven't done this for a long time, so yeah, almost forget. So then system does not lose energy. So the system, but here your psi is the state.
Yeah.
And then that is evolving.
Yeah, that evolves in time. Yeah.
But then that is evolving in time. But then the system contain all of the psi. I mean, I don't think I understand system does not lose energy over time.
Yeah, yeah. So this psi, yeah, represents the whole system. But in this case, yeah, there is no additional system that we're considering. It's just one system whose state is described by this psi vector. And this psi vector is time dependent and it evolves according to the Schrodinger equation. But it evolves in such a way that it respects the conservation of energy. So in that respect, the system doesn't lose energy with time. It's just.
So although the state is evolving, but the system doesn't lose energy.
Yeah.
Okay. Yeah. And also when you say you include environment in your total Hamiltonian, and then the environment, because the quantum system is always small, it's always been microscopic world.
Yeah.
And it will, once it become macroscopic, then it's already sort of lose the quantum coherence.
Yeah.
So it doesn't really apply to the whole universe because the universe is big. So it's even in the macroscopic world, then it's just become classical, and that's already the environment.
Yeah, no, that's a good point. Yeah, so yeah, it's true that like maybe let me just go back to the slides. Yeah, if I say here, so yeah, it's true that if your environment is macroscopic, it's going to be at least semi-classical. It's not going to exist in a quantum state. It's likely to have a kind of classical behavior. So a common approach actually is that when you use these system reservoir models, you treat the environment as basically an object that is just in thermal equilibrium. So it's basically just something that's in a kind of Gibbs state or the equivalent of that. So it's in that sense, the environment isn't kind of fully quantum, it's kind of semi-classical. But the important point is that it can still describe things like if you use this kind of explicit representation of the environment, it can give rise to behaviors that you can't describe classically. So for example, you can have spontaneous emission at 0 temperature, which, as far as I understand, that can't happen classically. Because you know, if you have something that's at 0 temperature, it doesn't exhibit any thermal fluctuations. you have these vacuum fluctuations that are specifically a quantum feature. Yeah.
Maybe two more questions. Yeah, please. And then you.
Sorry,
Okay.
this last paper you were talking about, where you said it was one of the first experimental sort of investigations of, you know, a truly quantum
Yeah.
open system. What kind of like physics, well, what physical system was being investigated? Were like
This one.
what kind of particles? What?
So it was using nitrovacancy centers in diamond. So it's basically diamond has I'm not a chemist or experimentalist, but I think so. Diamond has like this kind of crystalline structure, and you can have within that crystalline structure you can have these impurities, and I think that these impurities are called nitrovacancy centers. So they're kind of like nitrogen atoms that are embedded in this crystalline structure. The reason that people are interested in these types of systems experimentally is because they exhibit very long decoherence times. So basically, it means that you can manipulate these systems, and they can, you can use them to study quantum effects in a way that you can't with other systems, because other systems lose their quantum properties. So yeah, this is the kind of the physical setup of this. It's like just using, and the way that they manipulate the state, so the way that they, this cycle that they implement is kind of done through these kind of operations that are called U. So these U's are kind of, they just use like a laser to then change the state of the nitrovacancy center. Yeah.
Thank you.
You can just put the microphone.
Thank you. First of all, I would like to thank you for your talk today. Now,
thanks.
second, I don't in earth sciences, so I don't know much about quantum dynamics or mechanics.
Yeah.
But one of the reasons why I came here is that I expected, when they said a brief history, I was following like the chase about who's now best at quantum computing. So when I came here, I was expecting to hear Windows 1, Windows 2, Windows 3.
Oh, all right.
Yeah. But it turns out that it was a good thing that I came, because now I wanted to know, as with the equations you show, I wanted to question you, how does qubits relate to half particles? And then, but I think they 2 or 3, sorry for that. And then how does their relation, and if they are related, when you say it doesn't lose energy, do you mean like do they power themselves? Like,
so let me just answer your first question. So yeah, so this spin half example that I gave is effectively what a qubit. So a qubit is any quantum system that can only be in 2 possible states. And these obviously form the basis of a lot of quantum computing. So that's how information is stored in quantum computers, is using these qubits. So this system here is just a qubit. It's an example of a qubit. So your second point was about the energy powering itself. I mean, it doesn't, in a sense, power itself. So the system starts with a specified energy, and that doesn't change with time. So another way of thinking about this is like, for example, if you say, for example, you have a pendulum, something that just kind of swings back and forward. If you had this type of system but in a closed setting, so if you had no air resistance, you got any form of kind of damping or whatever, you place it in a vacuum, and you just left this system, this pendulum swinging, it would just swing indefinitely, just kind of undergo coherent oscillations indefinitely. So this is kind of what this system is kind of doing, kind of, but in a quantum sense, it's just oscillating indefinitely with time. So this system's not picking up energy from anywhere. It's just that it's not losing energy to anything. So that's what kind of...
I think the reason why I thought of that is because when you talked about open system and closed system, I take it that you said that the closed system is important is for you to be able to keep its quantumness. Like,
yes,
for you to be able for the quantumness. Now,
Yeah.
since that means quantum computers are already in a closed system, I think, because if they're in an open system, that means there's decoherence.
In an ideal setting, we would have quantum computers in a closed system. Unfortunately, it's really difficult to do that experimentally. So arguably, the reason that we like we do actually have quantum computers now. The problem is that it's kind of an issue of scalability. It's like if say you have a quantum computer and you want it to have loads of qubits, when you scale it up, it's really difficult to isolate it from noise. So the problem is that in an ideal sense, yes, we would have, if we were able to completely isolate these computers from everything, they would work the way that we wanted to, and we could scale them up to arbitrary numbers of qubits, and we would be able to solve Shor factorization. The problem is we can't do that because realistically, it's really difficult to stop noise entering in. So in principle, we want them to be closed. In practice, they're not closed.
Okay. Do we have any questions from online? No? Then considering the time, Graeme, I think we need to thank you very much for a very nice talk, very nice
Thank you.
introduction. Hope you don't have it.
No.
Our canonical with Arcu magazine.
thank
So
you,
thank
yeah.
you very much.
Cool.
And according to
Oh.
plan, there should be some snacks and drinks outside.
So I'll hold it up like this. Okay. Yeah.
Very much. Also, thank you